This is Specimen Paper 3, number 5, asks us to consider the infinite series and find the radius of convergence and the interval of convergence. When you see these convergence, radius, and interval, that should immediately make you think it's going to be the ratio test. It's only 4 marks for the first part when you find the radius. The interval of convergence is getting you more marks because you're going to have to test the endpoints to see whether they converge or not. And that's going to require different series tests that they can test other than just ratio tests in order to solve that. Okay, so the first thing you want to do is remember what your ratio test is. Okay, so your ratio test, which you use usually when there's n factorials, lots of powers of n, things like that, and also for radius of convergence and interval of convergence, you're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, find out where that's less than 0. Because this is where it converges. If it's greater than 1, it diverges. If it equals 1, that is the devil, because it means it is inconclusive, and we have to go find another series test to use. Okay, so that's like worst case scenario. But if they're asking you to find radius of convergence, this is the area that we're going to look for. Okay, so let's start with that test. All right, so we're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. We want to find out where that's less than 1. Okay, that's your ratio test. Okay, so here we go. We're going to take the limit as n approaches infinity. For a sub n plus 1, we are going to substitute n plus 1 everywhere you see an n. Okay, so that's n plus 1 minus 1 times x to the n plus 1 over n plus 1 squared, 2 to the n plus 1. Okay, it's divided by a sub n. That's the same as times the reciprocal. Okay, remember, this is a sub n. Okay, and that's your sequence that you have. All right, so we're going to do, instead of divided by it, we're going to do times the reciprocal. So n squared, 2 to the n, in the denominator n minus 1, x to the n. We want to figure out when the absolute value of this is less than 1. Okay, at this point, there's going to be some reducing that can be done. So let's look at the things that we can break down a little bit. Okay, this is obviously just n plus 1 minus 1. We have this x to the n plus 1, we have x to the n. So let's change this to be x to the n times x to the 1. That way we'll be able to cancel here in a minute. And we might as well just leave all this stuff. We've got n squared, we've got 2 to the n, all in the numerator. In the denominator, we have n plus 1 squared. We can separate this out to be 2 to the n times 2 to the 1. And then we have n minus 1 and x to the n. Okay, so now we can cancel our x to the n's. We can, what else can we cancel here? We can cancel, one more thing to cancel, the 2 to the n's. Maybe there was something else. Okay, and then just kind of look and see what we have left. See if there's anything we can do with that. Okay, so in the numerator I've got n squared, and x. So n times n squared will be n cubed, and I have x. In the denominator I have n plus 1 squared. I have that 2, and I have an n minus 1. Okay, if it doesn't have an n in it, then it's got nothing to do with the limit as n approaches infinity, and you can take it out. You could leave the 2 in if you wanted to, but basically the x at this point needs to come out. It has nothing to do with the limit as n approaches infinity. So the x has to come out. Up to you, but I guess I'll go ahead and take the 2 out. But everything left should just have n's in it or a constant. So I would have n cubed. In the denominator I have n plus 1 squared times n minus 1 less than 1. Okay. Now we want to evaluate this. The limit as n approaches infinity. Okay, if we look, if we expanded this all out, which you don't have to do, we just need to know what power is the n going to be to and what's the leading coefficient. So if you think about it, n squared times n is going to give you n cubed. The leading coefficient in the denominator is going to be 1. Okay, and so if this is n cubed, the highest power is n cubed, the highest power of the denominator is n cubed, you just take the leading coefficients, which in this case will be 1 over 1. Okay, so all of this guy turns into 1. So you have the absolute value of x over 2 times 1, if you want, is less than 1. Okay, so what this means is that x over 2 is between 1 and negative 1. And then all you have to do is multiply all 3 portions of this times 2. So you'd have negative 2 is less than x is less than 2. Okay, so what that means is the radius of convergence equals 2. Okay, think of it as a circle with 0 in the middle. You're going 2 up and 2 down from that. So that's your radius of convergence. We actually don't know whether it converges. It might converge on these endpoints, and that's what we're finding in the next part. Okay, so we have completed part A. That was the radius of convergence. So now we're going to do 5B. Okay, so part B, I just went ahead and rewrote again this series. We have already determined it converges between negative 2 and 2. What we want to do is test and see, does it converge on the endpoints or not? Okay, so I'm going to start by testing the positive x value first. Because if the positive x value converges, then this thing converges absolutely and will converge on both endpoints. Okay, so I'm going to start with that guy. So I'm going to start with x equals 2. So I'm going to take, well, let me just rewrite this. The summation from n equals 1 to infinity of n minus 1, substitute in 2 for the x. 2 to the n over n squared 2 to the n. Okay, well, the 2 to the n's cancel. So now what I'm trying to figure out is whether the summation from n equals 1 to infinity of n minus 1 over n squared, whether it converges or not. Okay, well, I could look at this. I could look at this as summation of n equals 1 to infinity. I could say n over n squared is 1 over n minus 1 over n squared. That'd be one way to look at it. Basically, we know about this guy. He is a p-series, okay, with p equal 1, and it diverges. So if I'm subtracting something from it, then I'm smaller than something that diverges, which tells me nothing. Okay, so what I'm going to do here is instead of just comparison, I'm going to do limit comparison. Okay, so I'll just bring that back up for you. Okay, so the comparison test is helpful here. If you're smaller than something that diverges, it does not help. Okay, if you're bigger than something that diverges, then you diverge. Okay, but the limit comparison test, if you'll remember, we're just going to put our particular series in the numerator over whatever it is we're going to compare to. We're going to see what we get. If we get a limit, they both behave the same, and then you can read the rest after that. So I'm going to try this with 1 over n. If you remember, when you're trying to compare, p-series is a pretty normal comparison, or with maybe a geometric series. But just compare. This is n over n squared if you get rid of all the small things. So that's the same as 1 over n. So 1 over n would be a decent series to compare this to. So I'm going to do the limit as n approaches infinity. I'm going to put my series over the series that I'm comparing to. Okay, so this would be equal to the limit as n approaches infinity of n minus 1 over n squared times n over 1, and this would give me n squared minus 1 over n squared, which equals 1. And that's okay. This isn't ratio test. This is us actually getting a limit. Okay, and so what this means, since we got something, okay, that means that both series behave the same. Okay, and since the summation of n equals 1 to infinity of 1 over n diverges, therefore our series diverges of n minus 1 over n squared diverges. Okay, and we will say that by limit comparison. With 1 over n. Okay, so we definitely know that the 2 endpoint is not included. What we have to check now is the negative 2. Okay, so I'm going to substitute in negative 2 in for the x right here. So it's going to look the same as this one, only it's going to have negative 2 right there. Okay, so this is going to be the summation from n equals 1 to infinity of n minus 1, negative 2 to the n, over n squared, 2 to the n. Okay, so this guy right here can actually be separated out to be negative 1 to the n times 2 to the n. Okay, and so if you do that, the 2 to the n's will just cancel. So what you'll have is a summation from 1 to infinity of n minus 1, negative 1 to the n over n squared. So this is an alternating series because you see the negative 1 to the n. So one of the things you can say is that if the absolute value of this series converges, then it will also converge if it's alternating. Okay? So in other words, if the absolute value of this guy without the alternating part converges, then it converges absolutely is what we call it. Absolutely just means it converges whether it alternates or not. Okay? However, I already know that it does not converge absolutely from above. Okay, we already figured out if this was just positive, then it's going to diverge. So the only thing left at that point, okay, is to test it with the alternating series test. In the alternating series test, you have to test two things. Okay, you have to make sure that the limit as n approaches infinity of your function is 0. Okay, and it definitely is. The degree of the denominator is larger, so this goes to 0. Now, we also know that's the nth term divergence test, so if it didn't, it would diverge anyways. Okay, and the other condition is that the this function itself, n minus 1 over n squared, has to be positive and decreasing. So check if this is positive and decreasing. Okay, so how can we do that? One way we can do that is graph it on the calculator. Look at it. Is it positive and decreasing from some point on? Okay, and the other way to do that, and if so, I would do a sketch and say that it was decreasing from some point on. Another way to do that is to test the derivative. Okay, so you could say f prime of x, and I'm just going to do quotient rule. Well, I guess I need to do x's, okay? So if these were all x's, then it would be low, d high, minus high, d low, all over low squared. So that would just be x to the 4th, okay? So this would be x squared, distribute, it would be minus 2x squared plus 2x over x to the 4th. And so then we would have negative x squared plus 2x over x to the 4th. If I took out an x, that would leave me negative x plus 2 over x to the 4th. And one of my x's could cancel, so I have negative x plus 2 over x to the 3rd. Well, so what we need to do is see if this is positive from some point on. If I put in 1, negative 1 plus 2 is going to be negative. This guy would be negative, definitely not positive. Okay, so we need to see what we're going to do here. Sorry, I just said that the opposite of what I meant to say there. If I put in 1, negative 1 plus 2 is 1. Okay, and so then you'd have 1 over x cubed, so 1 over 1 cubed, and that would just be positive. Okay, so where is the breaking point? Well, if you set the numerator equal to 0, you would find out that at 2, that's the break-even point, 0. And then from then on, if I put in, for instance, 3, negative 3 plus 2, then I would have negative over a positive. Okay, so this for n greater than 2 is negative, so decreasing. Okay, so this guy, and again, might be easiest just to graph this, x minus 1 over x squared, see if it's positive and decreasing, show them a little sketch on the graph. So since that function is positive and decreasing, then we can say, therefore, the series converges by the alternating series test, and there is your interval.